We can head right into it. So as I had mentioned before, I know some more have jumped on the presentation since, but my name's Dan Glavin, and I'm a regional sales manager with Dielectric. Prior to my involvement in the sales team with Dielectric, I spent a little over 3 years as an electrical engineer. The majority of my time through RFHawkeye was spent on designing new television antennas, radiation pattern studies for various FM directional applications, and the lion's share of my time during RFHawkeye was spent on the road. I did a lot of in the field commissionings of newly installed systems, and I think that throughout some of my experience in traveling and interacting with several different tower crews, you begin to hear the stories of some failures that have occurred in the field and some transmission line burnups and matchsticks in the sky, for lack of a better term. So I think that some experience in this actually adds a little value to the RFHawkeye presentation. So today I'll be discussing the importance of real-time broadcast system monitoring and the role in which Dielectric's RFHawkeye plays in the next generation of monitoring systems. I'll begin discussing common minor issues that are encountered in the field related to antenna and broadcast system installations and issues in those installations that can potentially lead to major issues and collateral damage. Next, I'll discuss the importance of current practices, but an overall emphasis on the shortcomings of current practices. Next, I'll discuss the approach to establishing the next generation monitoring system, and I'll close with an overview, if we have time, with a GUI demonstration of the RFHawkeye system here. So I'd like to begin this presentation out with a little fun video that I found online, and it's actually from you all's corner of the country, so you may be familiar with this. So I stumbled across this video on social media. It's a rather bizarre situation, but the end result is rather analogous to many occurrences that you all may have experienced with failures in the broadcast world. So like I mentioned, just kind of a funny video that I had stumbled across. This is for a microwave site, Bear Creek in California, and an acorn or a woodpecker or a squirrel decided to store all of their acorns inside of a microwave dish antenna. It's some background story on this is that they estimate that the accumulation of acorns took place over about 5 years. The owner of the antenna slowly noticed some degradation in performance and signal coverage until about 5 years later, they had complete failure. The radome was completely covered with about 50 pounds of acorns, and that caused that dielectric material caused a mismatch of the antenna, which elevated its VSWR and reflected power, and eventually the heat and et cetera got so bad that the antenna, it completely failed. So, luckily for this, it resulted in an inexpensive repair, but it results in system downtime. Move on to this next slide here. So this slide's about live monitoring and why it's necessary. The fundamental purpose of the RFHawkeye is to monitor the performance of a system's transmission line and antenna. Transmission line is the most vital component in a broadcast system, and it's most susceptible to damages due to the sheer length. Some of our towers in the United States are 2,000 feet of copper, so there are many failure points. The transmission line becomes susceptible to damage over time. The installation of the transmission line is a tedious but critical process that must be done with tremendous attention to detail. And that's very easy for someone like me to say that designs antennas from behind a computer screen comfortably on the ground. I'm not 2,000 feet in the air putting together a joint of copper transmission line. So as I mentioned, components and joints become susceptible to failures over time. The longevity of some of the critical components are a function of antenna usage and cycling. Constant cycling will cause expansion and contraction that will reduce the life expectancy of the copper transmission line that would otherwise last significantly longer. Each component in a broadcast system is handled by several people, beginning with the manufacturing and ending with installation. With this being considered, there exists an element of human error in the sequence from manufacturing to installation. While quality control and inspection deters many potential risks from entering the field, this too contains its own element of human error. Next slide here is about some minor field issues. The next few slides display instances of minor field issues encountered during installations. The reason that I have deemed these minor issues are because they were either visually recognized prior to installation or they were found by the commissioning engineer with a network analyzer, which essentially prevented catastrophic results had these components be put into operation. So I'll go through each one of these photos one by one. Some of these will be more familiar and some of you may have seen many of these and some may never. So this figure 1 shows a damaged and folded contact surface of the transmission line flange on a gas stop barrier. It's likely that this damage may have occurred in transit or during installation. The discontinuity of that folded over contact surface creates an variable that is susceptible to series or continuous arcing from the outer conductor of one piece of transmission line to the outer conductor of the next. Over time, the impedance mismatch will elevate and arcing will become more frequent as the metal continually deteriorates. This issue could evolve into sustained arcing and eventually lead to component failure and could potentially melt the Teflon due to excess heat and cause a complete system shutdown. This next picture is a rather often found issue in broadcast systems and coax transmission line installation. So this photo shows a transmission line connector with a pinched Teflon insulator. This insulator was pinched between transmission lines during installation. Similar to the Teflon, the O-rings can also become pinched between flanges and are equally as dangerous to the system. This pinched material introduces an undesired dielectric constant between outer conductors, therefore intensifying the electric field and breakdown voltage at this particular location. Depending upon the magnitude of the mismatch and the location, this issue may not be diagnosed during a system time domain reflectometry measurement or the system's commissioning. If this pinched Teflon was up toward the antenna input in an elbow complex with a stack up of reflection due to the phases of the elbow complex, it may be assumed that their reflection is normal. A couple of back-to-back 6, 7, 8-inch elbows are seen with a higher reflected power than a straight section of transmission line, so it may be considered negligible during a sweep. So that's when it can become potentially dangerous to the overall system performance. This next figure just shows some carbon that has built up on a Teflon insulator over time. The soot in carbon could be remnants of debris or dirt or some other contaminant that was left behind and not cleaned prior to powering the RF system on. Excessive buildup of this carbon, if gone untreated, can result in melting of the Teflon, potentially fire inside of the transmission line, and littering all the transmission line below it as well with this soot. So if the soot were to continue downward or upstream in the RF path, the damage can occur to the entire system and would not be localized to this individual area that can easily be cleaned up, replaced with a small bill of materials for the overall replacement here. The remediation process for this buildup of soot and carbon material consists of breaking each joint, which is rather time consuming, particularly in the Midwestern states where we where we have 1,500, 2,000 foot towers with a tremendous number of flange joints. So breaking each joint, sweeping off the debris, cleaning the Teflon with denatured alcohol, and then reconnecting the flanges prior to testing the overall system again. So, and this process will need to take place throughout the entire transmission line run. So the major issue is that in RF system failures is that when an issue occurs and it's investigated, the culprit has already typically gone up in smoke. It's burnt and turns into soot and falls down. Gravity helps to pull it down. So it's tough to find the original place of a failure inside a transmission line system. This next photo is a split bullet connector. The arrow in this photo shows that the anti-split ring or nose guard protector was actually still intact at the time of installation. And I have another photo here that shows that ring still intact. So what happens here is that the split finger reduces the insertion force of the connection between transmission line sections. That provides a nice snug fit and a constant impedance between transmission line sticks. What this also does is the location in which this finger is split off, it becomes closer to the outer conductor, therefore reducing the impedance and increasing the heat that this location will see. It also creates a smaller air gap between the inner conductor and the outer conductor, which could potentially push it past the breakdown voltage of air and cause sustained arcing that can litter the entire transmission line system as well. These are very common as well. We see these from time to time, pictures from installation crews, so it's not an unfamiliar occurrence. You see the anti-split ring there. Next portion of this presentation will be collateral damage. So collateral damage in the form of an undetected minor field issue can cause significant downtime to a broadcast system, hefty inspection and remediation and component bills. So some of these photos here, while not all that common, these came from a site that had an undetected minor issue that inevitably turned into collateral damage and replacement of the entire transmission line system. So I'll go into each one of these individually here. So figure 5 shows an anchor bullet connector with a melted Teflon insulator. So when that Teflon insulator burns and removes itself from the transmission line, the inner conductor no longer is stabilized and centered within that outer conductor. And it causes a fluctuating impedance mismatch. So it no longer is 75 ohms or 50 ohms, depending upon the desired impedance of the transmission line. But it actually fluctuates and therefore causes hot spots and an elevated reflected power from this location. So the debris from the melted Teflon coats the inner conductors and litters the transmission line below. And all of these pieces of debris inside the transmission line actually lower the power handling capability of the transmission line due to an undesired dielectric inside the transmission line. Here's another image, and this one's sort of a more powerful image showing the level of destruction that can happen when component degradation goes unnoticed. So the root of this pileup of inner conductors was a failed connector. So similar to the prior image, without a supporting connector component, nothing stabilizes, and the inner conductors cause a domino effect of falling downward due to gravity. And you can see by the rough cuts here, the inspection crew was actually unable to open any of these joints and remove components because they saw copper just blocking their way. So they took a Sawzall and cut across the flange in order to get that out of their way. This next image is a pileup of melted insulators and soot that resulted in the combustion that took place inside the transmission line. And you can see multiple inner conductors here stacked next to each other in a single outer conductor. This next image is to show the trickle-down effect that a serious fault can have on an entire system. This collection of Teflon, brass, and copper debris was gathered from on top of various Teflon pieces at different elevation levels in the transmission line run, as well as the elbow at the base of the tower. So this goes to show that an isolated fault can incur widespread damage and extensive downtime for system remediation. So the overall goal of this analysis of minor issues resulting in collateral damage is to prevent this from happening again. RFHawkeye as a product won't prevent failures in transmission line, but it will provide an early detection system of degraded components and frequent arcing. It can alert the user with a high level of accuracy to the location of the fault. The RFHawkeye has a plus or minus 18-inch accuracy for its degradation locating ability. So with RFHawkeye, preventative maintenance or investigation can be scheduled ahead of time based on the data that's taken from the trend of elevated VSWR that's taken from the real-time measurements of the RFHawkeye. And what can happen is that the investigation can be scheduled ahead of time rather than in an emergent fashion, which both mitigates cost associated with the maintenance and the window of time in which the maintenance will be performed. So a discussion about the current practices is important in understanding what these practices are intended to do, as well as where they fall short. Upon complete installation of an antenna and transmission line feed system, system test and commissioning is performed through TDR measurements. Once the system is given the seal of approval to broadcast at full power, the only continued monitoring system for the life of the system tends to be the forward and reflected power measurements that the transmitter continually monitors in a both pre and post filter directional coupler. Arc detectors monitor the occurrence of arcs within a system and log the data accordingly. So I'll go into a little bit more depth on these. So TDR measurements are performed while the system is off air. Under reduced power or small signal analysis from a vector network analyzer during a system's commissioning. The measurement is used to create a benchmark for the initial system characterization and to find anomalies that may be present due to installation issues. The TDR provides valuable information by localizing faults in the presence of impedance mismatches. The forward and reflected power monitoring of a system is analyzed by the transmitter and displayed by its display panel. These measurements are typically quantified as VSWR and can be conveniently displayed on the transmitter's digital output screen. This information can influence the decision of the chief engineer or a transmitter engineer or an alternate employee to shut down the transmitter due to uncharacteristic performance. And arc detectors, they're able to define arcing occurrences within a system. They also have the ability to interlock with the transmitter to reduce or discontinue transmitter output power. So however important each of these measurement practices may be, they each fall short to what is necessary in today's industry. The forward and reflected power measurement is an aggregate response of the entire system's performance. These results are difficult to interpret. It inherently cannot discern benign changes of an antenna performance due to environmental factors that change, such as icing conditions, rain, increased humidity. So those, they can't discern between the benign changes of an antenna performance to the dangerous, potentially dangerous changes inside the transmission line that's unaffected by environmental factors. TDR measures the response of a system under limited power. Under this limited power, anomalies can typically go undetected. The results can only be used as an initial characterization and cannot continue to compare and archive the system's performance to the benchmark. Performing this measurement requires a system shutdown and a field qualified engineer on your site. So the next generation of real-time monitoring system is to implement a system that can be retrofitted into existing sites. The RFHawkeye has the ability to detect and localize arcs due to changes in transmission line integrity. It will characterize a system over time. It will also allow for discrete alarms to be established by the user based on known component characteristics. Excuse me. This system consists of a coupling unit sensor, a power meter, and a control monitoring unit. The coupling unit is manufactured to the same transmission line size utilized after the transmitters or the coaxial switch to match the power handling capability of the unit to the overall system. The strategic placement of the coupling unit after the coaxial switch allows for the continuous monitoring of the system, whether or not it is in operation. So under full power conditions or completely dark. The results of this on and off air measurements can be very telling. It can identify temperature dependent mismatches by comparing measurements while the system is hot and after it's cooled down. Traditional TDR measurements, as I had mentioned before, can't achieve this because the system has already cooled down by the time the test setup is complete. So these hot versus cold measurements can be used as, you can take an approach to compare these in order to characterize the integrity of your system. The coupling unit consists of 2 injection ports, allowing for a wideband VHF signal to be injected into the system. The design of the injection ports is to couple the VHF signal onto the transmission line while nulling out as much of the broadcast signal as possible. So with that, the RFHawkeye operates independently of the broadcast transmitter itself. It has its own radar transmitter in its box that gets coupled onto the transmission line, sent up to the antenna, and due to the out-of-band nature of the signal compared to the passband of the antenna, the majority of that energy gets reflected back and is interpreted by the central monitoring unit of the system, and the data is both evaluated and manipulated to form a time domain reflectometry response of the system. So the RFHawkeye is an IP connected system. The nature of this IP connected system alleviates the monitoring duties necessary for individual broadcasters. Today, transmitter fail-safe circuitry is highly trusted and is the only method used for system protection. As I showed in the previous slides, collateral damage can occur because of the lack of alternative monitoring solutions to both verify and work as an emergency backup to the fail-safe circuitry. So when an arc is detected in a system, but the transmitter does not shut down, what's the plan of action as a broadcaster? Do we continue to broadcast on the main antenna and disregard the arcing event? Do we switch to, if we have the benefit of, do we switch to the potentially inferior aux system and schedule a maintenance on the main? If the arc incurs a shutdown of the transmitter, what's the plan of action then? Do we turn the transmitter back on and hope it was an isolated event? These questions become ambiguous with the presence of a real-time time domain monitoring system. The system can detect changes in return loss of less than minus 45 dB with a localization accuracy of actually plus or minus 8 inches. I believe I said 18 before. So a very precise degradation location. The system has also been tested and it meets or exceeds the FCC out-of-band spurious emission standards of less than minus 110 dB to carrier. And this system will also detect sustained arcs of greater than 100 microseconds. So here's a slide with my contact information here. If you have any questions about the RFHawkeye system, I've also put it into the chat box we have there. And both Ev and Kent, I'm not sure how we're doing on time here, but if there's any time available, I can do a brief graphical user interface demonstration.
Yeah, you should.
Great. So just give me a moment here. Excuse me. So just give me a moment to pull up a GUI of one of these units. We've been experiencing some network issues today, so let's just make sure I can get logged in. We sure can.
Tried to switch to that, but it wants you.
Yeah, it's just me.
It's just you.
Oh, well, nope, turn it on, I'll break it.
I'm doing line band.
Hello? I don't hear you, David.
Sorry, Keg, just having a technical difficulty here. Let me try to work on this in the background here, and I'll chime in once I can get the GUI demonstration.
Can you hear me
working
now?
here.
I do.
Oh,
Now watching the SBE meeting?
no, I got other things going on.
Yeah, with the network.
Is that you, Ben?
It's stabilized at the moment.
It's running now.
Is that you, Ben?
Maybe we'll get our Avid systems back up and running.
Mute Ben.
So while I'm trying to get a graphical user interface demo going here, I'm working in the background with our engineer, Tony Travellini. It appears that our network issues that we're experiencing are preventing me from accessing it remotely. Does anyone have any questions or discussion points based on the slides that I had? And I'll continue working on this in the background.
Sort of have one. I'm assuming this is for any broadcast work in the UHF, VHF bands, both FM radio and TV.
Correct. So the RFHawkeye has applications for all television, low band VHF, mid band VHF, high band VHF, as well as UHF, not only for the United States market of channel 14 to 36, but we can also expand that to the international stations that still go beyond channel 36, as well as FM. So the current offering is power limited. It's typically for high powered applications. And the reason for that is that the FCC out of band spurious emissions need to be carefully monitored, and the lower power of a broadcaster, the less headroom we have in that margin. So we are currently working on a low power application for this, but you are correct. All television and all FM applications can be accommodated by the RFHawkeye. And so I've actually been able to overcome my IT issues here. I'm going to go ahead and share a screen with you all again. Let's see. And if you all could just let me know if you can see my screen here.
Yeah.
All right, awesome. So here I'm logged in. I'm logged in with factory credentials into the user interface of an RFHawkeye system here. This particular system is KATV in Little Rock, Arkansas. It's just they are a Sinclair-owned station, similar to how Dielectric is owned by Sinclair. So the Sinclair has allowed us to utilize some of these sites as research and development over the last 4 years. So I like to typically show this KATV site when giving a demonstration. So when you first log in to the unit, you come to a dashboard, and this dashboard is configurable based on the measurements or the sensors that you have connected to the RFHawkeye. Currently, this dashboard just shows open alarms. Everybody loves to see no alarms in green. So what that means is there's no localized degradation in the transmission line. There have been no arcs in the last 24 hours, and that the antenna VSWR is within an acceptable value and beneath a warning threshold. So I'll just start to go through some of these menus on the side here and sort of give you a brief tour. So the best visual aid for the RFHawkeye is the degradation plot. And I'll go ahead and modify some of these parameters of the graph here so I can give you a better visual. So when you click on the degradation plot, here's what shows up. So the current measurement is in blue, and that measurement is taken and stored every 5 seconds. So the RFHawkeye can store data for upwards of 30 years based on the measurement interval. And this blue measurement will update every 5 seconds with a real-time response based on the forward and return signal of the radar transmitter. The yellow line here is a warning threshold, a warning threshold, as you can see in the legend on the right-hand side here. And that's a user-defined threshold. So if you know how your system should operate, and maybe in the summer it operates at a low VSWR, but then you get some icing over the winter and it elevates a little bit, but you've known it to be not an issue, you can set your threshold there. The red trace here is the alarm threshold, and that is also user defined, and it's typically a threshold that one will set that they want to be notified immediately, so that they can either reduce power, switch to an aux antenna, or start to make phone calls for an inspection of the system. And also on this legend over here to the right, you see these lightning bolts here. They will be shown on the x-axis here if there was an arc present in the system, but since we have no active warnings here, we don't see that. So if we go ahead and hover over one of these spikes here, here's what we'll see. So I know as a fact that this location here at 124 feet, give or take, is the 7-inch elbow at the base of the tower. I actually did the installation on this system here, and as we know, elbows have additional phase due to the discontinuity at the 90-degree bend, so they have a less optimal frequency response than just straight transmission lines. So as we hover over this location, it tells us the position in feet, 123.8, its current measurement of roughly 101.5 to 1 VSWR. And Dielectric also offers an algorithm that we've generated to automatically determine the warning and alarm thresholds here. And that's what has been established here. As you can see, the warning threshold for this particular component is 1.026 to 1 VSWR, an alarm threshold of 1.033 to 1 VSWR. So that kind of just dives into there a little. You see every time this turns green, the processing unit reading, and that coincides with the update to the graph as well. So up here in the top right, you see antenna status. So the RFHawkeye, it was originally a transmission line monitoring system, but we've added some forward compatibility to an antenna monitoring system as well. So what you see in the top right of your screen here in the form of a green shield and check mark in the antenna status is the forward power as measured on the Hawkeye's directional coupler, and the reflected power measured at the same location, converted into VSWR. And what this antenna status does and how it changes to in failure is that in the presence of a high VSWR, user defined, but in the absence of a transmission line degradation or arc, then it is determined that the issue lies at the antenna level. But an increased VSWR simultaneous to a degraded component in the transmission line or a detected arc does not actually indicate an issue exists at the antenna level. So, this forward compatibility to the RFHawkeye now allows us to monitor the entire system and not just the transmission line. So another metric of measuring is this 3D histogram here. Unfortunately, for demonstration purposes, it's rather bare, but fortunate for this station that there are no arcs. So it organizes the arcs here. I'll try to get a good view for you here. In the z-axis in the form of number of events, in the x-axis in distance from the output of the coupling unit, and on the y-axis in terms of time. So it will tell you where an arc occurred, when it occurred, and how many of them occurred. Another useful feature of the RFHawkeye here, we'll go into the power monitoring and trends. It shows sort of a speedometer of VSWR performance. It kind of like the antenna status on the degradation plot. It shows the forward transmitter power, the reflected power, and converts it to VSWR. and the red and yellow sections will automatically update based on the user input of what is an acceptable VSWR, what is a warning VSWR, and what is an alarm VSWR. And what it also does here, I'll show you, the last day or so of this particular system. So it will show you the trends of both the transmitter's forward power. As you can see, it's never truly stays at one power output due to increases in utility power and other arbitrary reasons as to why the power levels do increase and decrease over time. So you can see some noise involved in that, and that utilizes the right-hand y-axis, watts, forward power in watts. On the left-hand axis, it is VSWR, and you can see that the thresholds for this particular site have been set to 1.4 VSWR and 1.2 VSWR, and its actual performance is better than the minimum VSWR value on here of 1.036. Finely tuned system, great brand new transmission line, and it only measures forward of the RF system. So these numbers have been corroborated with Rody Schwartz power meters, etc. So yeah, this does show you kind of the archiving nature that the RFHawkeye can log for a system. And as I mentioned before, it can do this for up to 30 years. So on this particular system, the power monitoring are the only sensors included. The RFHawkeye can also support temperature sensors that can be mounted to a combiner, mounted to the outer conductor of a piece of transmission line, a temperature sensor that can just measure the temperature of your transmitter room or building. I know that some customers have had a high interest in that for some of their sites that are only accessed via helicopter or snowmobile in the winter. So that kind of gives you an indication of the HVAC system and how that's operating. It can also monitor the pressure inside of a transmission line by using a transducer in the NPT brass fitting in the gas barrier. So the RFHawkeye has a tremendous capability of monitoring all metrics of not only your transmission line and antenna system, but some of the ambient characteristics of your transmitter building as well. So I did kind of a brief graphical user interface overview here. As you can see, I'm connected via the web, so it's a completely IP connected system that can be accessed from anywhere in the world with a web browser. I'd like to kind of open the floor to any questions that any of you all may have at the moment.
Yeah, I've got a question about your transmission lines. If they get corroded on the connections and the transmitter, between the transmitter and the cable, it's severe enough, you replace the cable, or could you use some kind of cleaner to clean up the debris on the cable?
So Ken, I guess the answer to that comes with experience, and sometimes they can be cleaned up, but it depends on the how bad the issue is. On Teflons in particular, if you use denatured alcohol to remove some soot and clean stuff up, and if you see some discoloration of copper, some people tend to use Scotch-Brite or a lightly abrasive sandpaper. And if you see if some nicks have been put into brass flanges, contact surfaces, cable connectors, etc., sometimes people use a metal file to get rid of any sharp surfaces there. So it really comes down to experience, and it's tough to say whether all of these can be rectified manually, Kent. But if you ever have a question, the experience at the Dielectric factory, we have decades and decades of experience collaboratively of repairing these issues. Don't hesitate to send a photo over, and someone will get back to you on what they think, replacement or repair.
Okay, thank you.
Sure thing.
The alarms in this system just inform, they do not take action.
Not so sure I completely understood that. Would you mind repeating that question?
Do the alarms that are detected or the out of bounds operation, if detected, does it just send alarms, emails, or can it GPI, or what happens?
Understood. Thanks for clarifying. So in RFHawkeye's current configuration, it only notifies. It does require the end user to make the final decision in turning the transmitter off or reducing its power. So we don't currently offer a hard interlock from the RFHawkeye to the transmitter itself, but the RFHawkeye is SNMP enabled, so it can the MIB files of its SNMP can be integrated into, say, a BERT controller or an alternative controller of a transmission site in order to make those decisions to turn the transmitter off or reduce power. And what I will mention is that we do currently have that as a research and development topic in our engineering department to develop and integrate an input-output unit so as to interlock directly to the transmitter. But in its current offering, no, it requires the end user to make the decision.
Thank you.
Sure thing.
I have a question about your monitoring system that you're using on the RFHawkeye, where you're using an RF signal up to your transmitter using different frequencies of it. And is it a low powered, or is it the same power as the regular transmission line?
So the signal on the RFHawkeye, great question. So a little bit, I won't go too into the weeds on the RFHawkeye signal, but what I'll answer your question directly. The RFHawkeye has the ability to put out 2 watts of VHF power. So it utilizes a frequency band outside of the high band VHF, as well as outside of some of the maritime communications, so as to mitigate any interference issues. And it can output up to 2 watts, but the determined output power of the RFHawkeye are based on factors inherent to the transmitter, to the transmission system itself. What is the it's dependent upon the length of transmission line, and the reason for that is the losses. Length of transmission line due to the losses and the time and distance at which the radar signal will overlap itself and potentially contaminate the data that's obtained. The power level of the broadcast transmitter. And so what we've done is in the user interface here that can only be accessed with our factory credentials, the equation has already been built in. So when we plug in some inherent parameters to your transmitter or transmission system, it will automatically calculate and set the transmitter output power for the RFHawkeye monitoring system. So I think that answers your question. And just to dive in a little bit more, you know, the RFHawkeye signal is a pseudo-random bit sequence, so it is not a continuous signal. It is a modulated signal here. And back to sort of the power levels, you know, those are determined based on the parameters so as to meet the FCC out of band or spurious emissions standard of 110 dB down to the carrier. Does that answer your question in full?
Yes, it did.
Awesome.
Thank you.
Of course. So we currently have 18 RFHawkeye systems integrated throughout the United States. We partner with a company, DAC System, which is an acronym, Direct Antenna Control System, out of Switzerland. And their name is pretty self-explanatory as to what they do. DAC has taken the lead on antenna system and broadcast system monitoring, and they approached us a few years ago to collaborate on this real-time full power monitoring system. And you know, the number 18 systems being integrated into the field may sound somewhat underwhelming to most, but we've actually only been offering this for about a year now outside of the Sinclair environment. We spent a tremendous amount of time on research and development and compliance statements, compliance calculations. I personally spent a significant amount of time with some consultants taking measurements and repeatability precision and accuracy to make sure that this VHF signal is within compliance and isn't broadcasting out of your narrow band antenna and interfering with any adjacent broadcast operations you have around. So a tremendous amount of time was spent in compliance and research and development. And, we're happy to be past that stage and now in the stage of trying to get these out to, all of the broadcasters where the climate has changed with remote employees, added tasks to current employees, where they can't get to a transmitter site all that often. This Dielectric's also working on a centralized monitoring platform called Analytics, which is a centralized platform with access to all of the RFHawkeye units in a web browser. So you can simply surf to a web browser, see all of your units within your network, instantly see their status based on green means go, red means problem, and double clicking on those units, and it will bring you directly to the screen I'm sharing over here, but for your particular unit. So we do plan to have deployment of that centralized monitoring platform in about the next 8 weeks. And it'll be a very good tool for not only broadcasters at the local level, but at the corporate level, as well as for our team of engineers that will form as a knock in the long term if that service is so desired from the user end. So I spoke a lot about the RFHawkeye today. I'd be happy to reply to any emails. If anyone else has any more questions, feel free to go ahead and have them come in. I'll kind of sit here and see if anyone has anything to say on this. But I'd just like to, again, say thank you to both Kent and Ev for inviting me to talk with you all today. I've yet to make it in person to an Oregon SBE chapter meeting, and I hope the climate of the world creates a more conducive environment to that in the future here. So for the moment, I'll stop sharing my screen and see if anyone has any questions.
Eugene,
Anybody?
a question came up from Eugene of a rough idea of what the cost of the system might be.
Yeah, great question. So Kent, what I'll do, I'll describe it on here, but Kent, I'll send you another email with a little price list just in case you want to maybe distribute it to the attendees today or your chapter. I know you guys are rather active, which is nice with emails, but for a single or adjacent combined station UHF system for channels 14 to 36, the rough cost is about $27,000. For broadband panel antennas in the UHF, the price does increase based on power levels. And the FM and VHF systems are priced rather comparably to the single channel or adjacent channel UHF station. So, RFHawkeye does have a price tag to it, but we see it as an additional employee. It's a constantly monitoring system that kind of reduces the duties and day-to-day tasks of a chief engineer or station engineer that's stretched thin already.
Because some of the stuff I've been looking at in these recently, that's a drop in the bucket.
Yeah, when you compare it to say 2,000 feet of 6-inch transmission line, that's $400,000. A $27,000 system that can give you early detection versus burning up 2,000 feet of copper. I would agree with your drop in the bucket statement there.
Or the antenna that's even more.
Exactly.
Well, I want to thank you for your presentation today. It was quite informative.
Yeah, thank you very much for having me. It was a pleasure to join you guys today and talk about this. Well, I hope you all that are in person together are able to enjoy your lunch, and nice to see some people face to face, and hopefully I can I can join that here in the short term. And for everyone that joined in remotely, thank you as well. And it was a pleasure talking with you all today.
Any words,
Okay.
Dennis?
Yes, thank you from the Eugene Chapter 76. We appreciate you very much taking the time to make the presentation. I think you did a terrific job. Quite an interesting piece of equipment.
Thank you very much, Dennis. My pleasure.
Dan, you said this was not suitable for like a lower power. I mean, what's the threshold there? I mean, I have a lower power that's like 1.3 kilowatt forward and, out of the transmitter.
So you know what? That's a great question, and some additional parameters will need to be considered in order to do the spurious emissions calculation. So if you'd like to send me an email with your transmission line length and your transmitter power output, which you said 1.3 kilowatts, I can go ahead and do a calculation here for you. But off the top of my head, I don't believe that those power levels will pass spurious emissions. And as for the threshold of what is high and low power, it's tough to narrow in on as well without the complete set of information there.
Yeah. And then you also said this is generally installed like after in my case, I have that patch panel going between
Okay.
the transmission line and the dummy load.
Okay. Yeah, so sorry, go on.
You would put that like in line right after that.
Yeah, so what I like to do is, so the coupling unit itself is not pressure tight, so it needs to be installed prior to a gas barrier, so as to maintain pressure in your transmission line up to your antenna. And I like to install it as close to the transmitter as possible, but there are some caveats there. So because it operates on a VHF signal, it has to be downstream from any waveguide components, because waveguide acts as a short circuit for VHF and doesn't promote propagation. So it has to be after any waveguide components, but as close to that point as possible, because if you have a monitoring system, you want it to monitor as many components as possible. So my recommendation is as close to the last waveguide component, but before the gas barrier in an unpressurized section of transmission line.
So it's fine to go through the bandpass filter and all the directional couplers.
It can't go through the bandpass filter because the signal of the radar transmitter is 125 megahertz in bandwidth. And the reason for that is it allows for the resolution in the measurement to identify the individual components. So if it were to pass through the band filter, it would only promote 6 megahertz of signal propagation, which would substantially diminish the resolution there. So, but all of the other non-frequency dependent components, it can propagate through.
Yeah, that's what I was wondering, because I think I have an arc in my patch panel. And I was like, well, if I put it after that, it wouldn't have detected it.
Is that so? If you gathered my email address from the chat, I'd love to talk with you a little bit more about it if you don't mind sending me an email.
Yeah, I will. I gotta do some recon tomorrow, and then I was going to email you with more details and photos.
Awesome. If you have a thermal, if you have an infrared camera or a thermal imaging, that's a great way to detect some issues in your system. I know your power levels may not show heat that well, but even an anomalous localized increased temperature could show you where to pull the patch panel apart and take a look for any evidence of arcing.
Okay, thank you.
Awesome. All right, everyone. Well, I thank you again. I hope everyone has a nice rest of their afternoon, and don't hesitate to reach out with with an email for a request for any more information on RFHawkeye, or if anyone has any component needs there. I'd be happy to help you with anything I can.
Great, thank you.
Thanks, everyone. Take care.